through some applications, we will see few different types of semiconductor devices, and then finally we will have a brief history of power electronics. So first question is, what is power electronics? Power electronics can be defined as the use of electronic devices to control and convert electric power. Therefore, every application of power electronic will involve some aspect of control in it. From household electronics to equipments in space applications, they all will have some sort of power electronic devices in them. Power electronics have already found an important place in modern technology and are now used in a great variety of high power product. Various types of controls such as heating control, light control, etc. Then we have power supplies, vehicle propulsion systems, and high voltage direct current or HVDC systems. Power electronics are found virtually in every electronic devices. The power electronic, the field itself refers to an interdisciplinary subject which deals with design, control, and conversion of power in its electric form. In power electronics, we are dealing with multiple disciplines such as circuit theory, systems and controls, signal processing, simulation and computing, solid state physics, electromagnetics, electric machines, to name a few. Then, since the power electronics itself is a disciplinary area, one needs to have knowledge in the following areas to understand power electronics completely. So very first one is electronics. So in electronics, we are looking at semiconductor devices, their protection, gate drive circuits, power supply designs, circuitry, etc. Then in the control part, we are looking at closed loop control systems, continuous or discrete systems available. And then the third one is power systems. So here we are looking at static and rotating power equipments, motor drives, traction controls, etc. Some of the areas where power electronics is utilized are listed here. Power electronics are found in motor drives of pumps, blowers, and mill drives for textile, paper, and cement industries. They are also found in traction motors of electric vehicles. They are used in electrolysis process equipments, arc welding machines, furnaces, ovens, and lighting systems. Application of power electronics is very vast, and these are very few applications which we can see here. Then semiconductor devices can be classified in terms of their controllability in three groups, which are first controlled, second semi-controlled, and third controllable devices. So here are some examples of power electronics switching devices. We'll go through them one by one. So first is the power diode. It is a form of uncontrolled semiconductor device. So they cannot be turned on or off. So they are turned on or turn off when certain conditions arise in the circuit. So you cannot control their turn on and turn off. So that's why they lie on the first segment, uncontrolled devices. Then the second one, we have a semi-controlled devices. So these semi-controlled devices, they can be turned on, but their turn off is not controlled. So one of them is thyristors. Thyristors are semi-controlled devices. They can be turned on, but their turn off is not controlled. Turn off is achieved either naturally when the current decays to zero, or by forcing the current to deviate to another component. We will see how this is done, but for now just understand that thyristors are semi-controlled devices which can be turned on, but their turn off is not controlled. And then we have the third type of devices which are fully controllable. These devices can be turned on and turned off by some provision, for example gate control. So the example of these type of devices are transistors. Transistors are controllable devices. There are multiple types of transistors available, such as power transistors, BJT or bipolar junction transistor. Then we have metal oxide semiconductor field effect transistors, abbreviated as MOSFET or MOSFET. And then we have IGBT or insulated gate bipolar transistors. Further, we can classify these power electronic switching devices according to their specific characteristics and requirements. So based on the continuous gate signal requirement, we have BJT, MOSFET, IGBT, and then we, based on the pulse gate requirement, we have SCR or silicon controlled rectifier, and then we have the GTO or gate type GTO is type of a thyristor. And then with respect to their current capabilities, we have bidirectional current capability in triac, which is again a type of thyristor. And then we have a unidirectional current capability of SCR, GTO, BJT, MOSFET, IGBTs, etc. So moving on to the brief history of power electronic devices. Power electronic devices started with the development of mercury arc rectifier, invented by Peter Cooper Hewitt in 1900s. It was used to convert alternating current AC into direct current DC. The first thyristor devices were released commercially in late 1950s. A breakthrough in power electronics come with the invention of MOSFET or the metal oxide semiconductor field effect transistors. The power MOSFET is the most common power device in the world due to its low gate drive power and fast switching speeds. But in 1982, the insulated gate bipolar transistor or IGBT were introduced. It became widely available in 1990s. So IGBTs have the power handling capability of the bipolar transistor and the advantages of isolated gate drive of the power MOSFETs. So IGBT will takes best from both these things, from the bipolar transistors as well as the power MOSFETs, and include them into the IGBTs. And then we have the developments in display signal processing or DSP, and their dedicated microprocessors. So they lie parallelly with the microprocessor designs. Thank you. In the previous video, we discussed briefly about power electronics, defined the term, saw its interdisciplinary nature and few applications. In the end, we went through some power electronic switching devices. Now, in this video, we are going to look at each of these power electronic devices in detail. Modern power electronic devices can be classified in a number of ways based on their number of terminals, the number of PN junctions, level of controllability, bidirectional capability, and the gate signal requirement, to name just a few. Taking the number of terminals, power electronic devices are broadly divided into two groups. The first group is of 2-terminal devices and the second group is of 3-terminal devices. The 2-terminal devices are such devices whose switch state solely depends on the externally connected circuit. The diode and diac are prime examples of the 2-terminal device categories. Now, the 3-terminal devices consist of the thyristor and the transistor. These devices are such devices whose switching state does not solely depend on the external circuit, but it also depends on the driving signal at their respective gates. Based on their controllability, they are classified into 3 groups. First one, the uncontrollable switches, second, semi-controllable switches, and the third, fully controllable switches. The uncontrollable switches consist of the diode and the diac, just like the 2-terminal classification, which is based on their number of terminals. These switches are in this class because the turn on and the turn off cannot be controlled and is solely determined by the external power circuit. The semi-controllable switches can be turned on but cannot be turned off directly from the gate. In this category, the thyristor, specifically the silicon controlled rectifier or SCR, and the triac are prime members of this group. And the last group of members consist of fully controllable switches such as BJT, MOSFET, GTO and IGBT. Before moving on with the power electronic switching devices, let's understand what an ideal switch is. This will set a benchmark to compare in further slides. So an ideal switch should have no voltage drop in on state. This is the first characteristic, and the second being the zero current during off state, and the third very important one is there is no power loss in both on and off states. But now these characteristics are for the ideal one. They are very hypothetical and cannot be replicated or cannot be fully replicated into practical life. So in practical life, there are voltage drops, switching delays and switching losses between the switches, as you can see from this figure. Moving on, let's start with the uncontrollable switches. Diodes are formed from a PN junction of semiconductor material. They generally have two terminals, one being anode and the another being cathode. A diode is an uncontrollable and unidirectional switch, hence its operation is determined by the direction of the flow of current in the circuit or the flow of current in the external power circuit. Right. So a diode is basically a short circuit when it is forward biased, that is when the current is flowing from anode to cathode, and conversely it is an open circuit when it is reverse biased, that is when the direction of flow of current is in the opposite direction in the circuit. Application of the power diode include rectifiers, clipper circuits and many more. Some of them are listed in this slide. Now moving on to the second class or second category, semi-controllable devices. In semi-controllable devices, one family is very dominant, which is thyristor family. The thyristor family of power electronic switches are of 3 terminals, 4-layer semiconductor devices. The 4 layers of a thyristor are made up of 3 alternating PN junctions. Some of the prominent members of the thyristor family are SCR and GTO. While SCR is a semi-controllable type, GTO is from the fully controllable group of power electronic switches. And a SCR is a unidirectional switch just like a diode, but it has gate terminal which controls its turn on. So basically the SCR you can turn on by providing some voltage into the gate, but you cannot control its turn off characteristics, which again makes it similar to diode and depends solely upon the external power circuit. Now let's look at some mode of operation of SCR. First is the reverse blocking mode. Here voltage is applied in such a direction that will be blocked by a diode. So here SCR basically will act like a diode. Now the second mode is the forward blocking mode. Here voltage is applied in such a way that will cause any diode to conduct, but the thyristor will still stop the conduction because it is yet to be triggered via gate. Once triggered via the gate, it will start conducting and will remain conducting until the forward current drops below a threshold. That is, now this is the third mode of operation of the thyristor, or to be very specific, SCR. Although the thyristor quickly gained traction in many AC applications such as AC drives, uninterruptible power supplies or UPS, its turn off incapability and the low frequency of operation limited its applications. In this video, we saw two power semiconductor switches, first diode and the second being the SCR or from thyristor family. In the next video, we will move on to the fully controllable power electronic switches. Thank you. In the previous video, we started with the classification of power electronic switches based on their number of terminals as well as based on the number of their degree on controllability. Later on, we discussed power diode and thyristor, specifically SCR, in detail. In this video, we will be moving on to fully controllable class of power electronic switches. Now, these fully controllable class of switches will include several devices depending upon multiple factors. Now, some of these devices are bipolar junction transistors or BJTs. There are MOSFETs, there are gate turn off GTO thyristors, and then we have insulated gate bipolar transistors or commonly known as IGBTs. There have been major advances in recent years in these category of devices. Now, these devices can be turned on and off by control signals applied to their control terminal of respective devices. Now, an ideal controllable switch should have a specific characteristics which we will be defining in the next. So these class of devices should block arbitrarily large forward and reverse voltages with zero current flow when off. They should conduct arbitrarily large currents with zero voltage drop when they are on. They should switch from on to off or vice versa very instantaneously when they are triggered. And now the final one, they should use vanishingly small power from control source to trigger the switch. Now, as expected, real devices do not have these ideal characteristics, and hence they will dissipate power when they are used in numerous applications we have mentioned earlier. And also, depending on the devices, there are different control signal requirements as well. We will look at these devices one by one. We will begin with the GTO or gate turn off thyristor. GTO is very similar to SCR except that it can be turned off at a gate, which SCR couldn't. The turn-on operation of the GTO is very similar to a thyristor when an anode terminal is made positive with respect to the cathode. By applying a positive gate current, the whole injection from the gate forward bias to the cathode pin junction happens. Now, but unlike a thyristor, it can be turned off when a reverse bias is applied to the gate, which will make the gate negative with respect to the cathode. The GTO or the GTO thyristor suffers from long switch off times, whereby after the forward current falls, there is a long tail time where residual current continues to flow. Now this happens until all the remaining charge from the device is taken away. Now this particular thing will restrict the maximum switching frequency to about 1 kilohertz. Now it should be also noted that however that the turn off time of a GTO is approximately 10 times faster than to a comparable SCR. So they are still very fast compared to SCR, but again they are limited by something. Although this will solve the problem of conventional thyristor, but it comes to its own unique challenges such as it has poor turn off gate current gain, and the second breakdown problem it exhibits at turn off. So it also has a limited operating frequency of less than 5 kilohertz, and the gate drive design is quite complex because it needs to account for a large reverse gate current to turn it off. The main applications are in variable speed motor drives, high power inverters, and traction. Now GTOs are increasingly being replaced by integrated gate communicated thyristors, or short form of their IGCT, which they are commonly known as. Now these are an evolutionary development of the GTO itself, and also they are being replaced by the transistor family, or specifically we can say IGBT, the insulated gate bipolar transistors, which are which is a member of transistor family in replacing the GTOs in many applications. Now the next device we will be looking at is BJT, or a bipolar junction transistor. BJT or bipolar junction transistor is a 3-terminal, 3-layer, 2-junction semiconductor device. Now the name of these terminals of this device are emitter for E, base for B and collector for C. When two PN junctions are combined together with a central layer of semiconductor being common to the outer two layers, they will form either a PNP or NPN type of transistors. Now since it will both use electron and holes as charge carrier, it will get its name the bipolar junction transistor or the BJT. In NPN type of transistor, the current flow from collector to emitter when the base is supplied with a positive voltage, while in case of the PNP transistor, the current direction is reverse, that is from the emitter to the collector when the base is supplied with a negative voltage. Since in NPN transistors, majority carriers are electrons and minority carriers are holes, the transistor will turn on when electron enter the base region, while in case of the PNP transistor, here things are reversed. Majority and minority carriers are holes and electrons respectively. Thus, the transistor will turn on because of the movement of holes into its base. In order to understand this, you just simply have to have a better understanding of the PN diode itself. The construction of the power transistor is different from the single transistor. Uh, so the power transistor will be structurally different compared to a normal BJT. So depending on the application, the construction is different. Now the only difference is that the N layer is added in the power BJT, which is known as the drift region. Now let's quickly understand the structure or changes between the normal BJT and the power BJT. A power BJT will have a 4-layer structure of alternating P and N type of doping as shown in the figure. It again have the same 3 terminals labeled as collector, base and emitter. In the most power electronic applications, the power transistor works in common emitter configuration. That is, base is the input terminal and collector is the output terminal, and emitter is common between output and input. In power switches, NPN transistors are most widely used compared to PNP transistors. The thickness of the drift region determines the breakdown voltage of the power transistor. The characteristics of this device is determined by the doping level in which the layers and the thickness by which the layers are fabricated. In the next video, we will look at 2 other fully controllable power electronic devices, which are MOSFETs and IGBT respectively. Thank you. In the previous videos, we started with the classification of power electronic switches based on the number of terminals as well as based on the number of degree on controllability. Later on, we discussed power diode, thyristor, and in the next video, we went through GTO and BJT as well. Now let's move on to the last but not the least type of controllable switches, which are MOSFETs and IGBTs. The first one is the MOSFET, or the full form of MOSFET is metal oxide semiconductor feed effect transistor. It's commonly referred as MOSFET. So here onwards also we will refer to this as MOSFETs only. MOSFET is developed by combining the areas of field effect concept and MOS technology, or metal oxide semiconductor technology. The conventional planar MOSFET has the restriction of handling the high power. So in high power applications, the double diffused or the vertical MOSFETs, or they are sometimes called as VMOS, is used, which is simply we can refer to as the power MOSFETs. The power MOSFET is a 3-terminal, 4-layer, unipolar semiconductor device. So let's see what it is. So being 3-terminal, it has a gate, drain, and source terminals. It is a 4-layer of type, so N, P, and N type. And then we have since it is the only majority carrier in conduction, so it is unipolar type of device. The MOSFET is a majority carrier device, and as the majority carrier devices have no recombination delays, the MOSFETs achieve extremely high bandwidths with switching times. Now, the gate is electrically isolated from the source, and while this thing provides the MOSFET with its high input impedance, it also forms a good capacitor as well. MOSFETs do not have secondary breakdown area. Their drain to source resistance has a positive temperature coefficient, so they tend to be self-protective as well. MOSFETs has a very low on resistance and no junction voltage drop when forward bias. These features make the MOSFETs an extremely attractive power supply switching device. So that's why they are used almost everywhere. Now the symbol for the N channel MOSFET is given here. The direction of the arrow on the lead that shows the body region will indicate the direction of current flow. As this is a symbol for N channel MOSFET, the arrow is inwards. Now for the P channel MOSFETs, the arrow will be outwards, towards the outward side. Now let's quickly go through the structure of the power MOSFET. The power MOSFET has a vertically oriented 4-layer structure of alternating P and N type of layers. The P-type middle layer is called as the body of the MOSFET. In this region, the channel is formed between the source and drain. The N layer is called as the drift region. Now this drift region will determine the breakdown voltage of the device. This N region is present only in the power MOSFETs and not in a single level MOSFET type. The gate terminal is isolated from body by silicon dioxide layer. When the positive gate voltage is applied with respect to the source, the N-type channel is formed between source to drain. Now this is shown in the figure that there is a parasitic NP and BJT between source and the drain. Now to avoid this BJT turn on, the P-type body region is shorted to source region by overlapping the source metallization on the P body or the P-type body of the MOSFET. The result is that a parasitic diode, now this is being formed between the source and drain terminals. This integral diode plays an important role in half and full bridge converter circuits. Now the power MOSFETs are extensively used as a part of the power supplies. They will have a very good application on DC-DC type of converters, and then they are used in the low voltage motor controllers as well. Now moving on, the next type of device which we are looking is IGBT, or insulated gate bipolar transistors. So the IGBT is a relatively new device in power electronics, and before the advent of the IGBT, power MOSFETs and power BJT were commonly used in power electronic application. Both of these devices possessed some advantages and simultaneously some disadvantages as well. On one hand, we had bad switching performance, low input impedance, secondary breakdown, and current control power BJTs. And on the other hand, we had excellent conduction characteristics of it. Now similarly, power MOSFETs have the excellent switching characteristics, high input impedance, voltage control power MOSFETs as well. Now but at the same time, they had bad conduction characteristics and problematic parasitic diode at higher ratings. Now, though the unipolar nature of the power MOSFETs will lead to low switching times, it also leads to a high on resistance or on state resistance as the voltage rating goes on increasing. Thus, there was a need for such a device which had the goodness of both. So they should have a goodness of the power MOSFETs and goodness of the power BJT as well. Now, this is when the IGBT was introduced in around early 1980s, and this became a very popular among the power electronic engineers because of its superior characteristics over power MOSFETs and power BJTs. Now, the IGBT will have the power input characteristics of a power MOSFETs and the output characteristics of the power BJT. So, best of both worlds. So, uh, the good things of the power MOSFET and the good things of the power BJT was combined, and IGBT was made. Okay, so therefore, since it was a basically a combination of these two devices, they had a symbol of amalgamation of both of the parent devices. So the symbol of IGBT you can see here, and then the three terminals of the IGBT are gate, collector, and emitter. Very basic in the transistor type or transistor family of devices. Now, IGBT is known by various names. So they are also called as metal oxide insulated gate transistors, or MOSIGTs. Sometimes they are called as gain modulated field effect transistors, GEMFET or GEMFET. Also, sometimes they are simply referred to as insulated gate transistors or IGTs. Now moving on to the structure of the IGBT. The structure of the IGBT is very similar to that of a power MOSFET. So, except there is a one layer known as injection layer. Now this injection layer is basically like a P plus unlike N plus substrate in the power MOSFET. So this injection layer is the key to the superior characteristics of the IGBT. Other layers are called the drift and the body region. Now two junctions are called as J1 and J2 junctions in the structure. Now the N channel IGBT turns on when the collector is at a positive potential with respect to emitter, and gate is also at a sufficiently positive potential with respect to the emitted. Now this condition leads to the formulation of an inversion layer just below the gate, leading to a channel formation, and a current begins to flow. Now this will lead to a flow of current from the collector to the emitter. Now the collector current in IGBT will constitute of two components. The first one is due to the injected electrons flowing from collector to emitter through the injection layer and the drift layer, and finally the channel is formed. The other current, or the whole current, which is flowing from the collector to emitter through the body of resistance body. A peculiar phenomenon is observed in IGBT. Now this is known as the latching up of IGBT. This occurs when a collector current exceeds a certain threshold value, which is predetermined. Now in this, the parasitic thyristor will get latched up and the gate terminal loses control over the collector current, and the IGBT now will fail to turn off even when the gate potential is reduced below the certain voltage. Now for turning off the IGBT, we need a typical commutation circuitry, as in case of a forced communication for thyristors. Now if the device is not turned off as soon as possible, it may get damaged, and once it gets damaged and we cannot control the power on and off, it can damage the whole electronic circuitry and the device as well. Now moving on to the advantages and disadvantages of the IGBT. Now advantages are quite compared to the power MOSFETs and power BJTs. The advantages are it will have a lower gate drive requirement, it will have low switching losses, it has a small number circuitry requirement, it has a high input impedance, temperature coefficient of on state resistance is positive, and when we compare to a power MOSFET it is less, and hence it will have a low on state voltage drop and power loss. It has a better safe operating area compared to the other class of devices. Now the disadvantages are the IGBTs are very costly, they have a latching up problem, and it have a high turn off time when you compare it with a power MOSFET. Now to draw a conclusion the power electronics devices which we saw, it is important to compare these devices. Now, some of the most prominent of them we have studied. We have studied GTO, we studied BJT, we studied SCR, MOSFETs, and IGBTs. Now, comparing to GTO to SCR, the GTO triumphs the SCR due to their faster turn-offs. Their use result in increased converter efficiency. There is an elimination of the need for commutating components. Now, there is also reduction in electromagnetic and acoustic noises as a result of elimination of chokes. Now, GTOs also have a high on-state gain, ratio of peak surge to current, and higher voltage blocking capabilities when you compare the GTO to BJT. However, GTOs require snubber to operate normally, and snubbers for high power applications are quite expensive. So the high on state voltage drop in GTOs coupled with the high gate current requirement and the high losses in the gate drive are quite a number of demerits for the GTO. The MCT seems to be an improved GTO, seeing it has a lower forward voltage drop, a higher current density, and an improved gate technology, hence making it easy to control. On the side of the transistors, the IGBT, which combines the advantages of MOSFET and BJT, seems to be the champion of the transistor class of devices. It has a simple gate drive circuit and will require a small amount of energy at switching, which is the result of its high gate impedance. Although it has a lower switching speed when compared to MOSFETs, its current and voltage capability is higher than that of BJT and MOSFETs, especially when we are comparing them one to one. The MOSFET has a higher switching speeds and has the potential to be the most effective parallel switch. Now, in case for the SCR, the SCR has the highest current and voltage ratings and overcurrent protection that can be achieved via a fuse. The IGBT as well as the MOSFET have some of the easiest gate drive features among the type of switches we have studied. Now, summarily, the different power electronic switching devices, although compete on several levels, they will still possess a unique characteristics that make them suitable for a very uniquely specific application. So we have to have an understanding of all of these devices so we can choose which device is very uniquely suitable for our application. Now, having said that, the IGBT and the MCT shows a lot of promise when looking at the transistor and thyristor families of power electronic devices respectively. Now, one major difference that can be quickly observed is that the devices with relatively large power capabilities have comparatively low frequency of operation when compared to the devices with significantly lower power capabilities. So there is still a room for continuous improvement and advancement in power electronic switches, as their applications can be continuously improved as the switches get better and better by the years. The future of power electronic switches is brighter with the introduction of wide bandgap technology. Now, this is a very new type of technology we are seeing here. So it is even more promising considering the amount of research going on to the ultra wide bandgap semiconductor materials. Now, although the technology of ultra-wide bandgap semiconductor is still immature in a very early stage, it shows a lot of promise as the materials forming this class of semiconductors will have bandgap up to 6 times that of the silicon. So they are intuitively they are very much where the devices which will be using this type of semiconductors will have a very better characteristics compared to the silicon family. Thank you.